Geometric progressions are just the next step on from arithmetic progressions, really. They're not covered at GCSE, but they follow the same rules, the same principles, and you'll get the same sort of problems as you would with your arithmetic progressions. So geometric progressions are where there is a common ratio rather than a common difference. So we're saying that if we begin with one term, for example, 3, we're going to multiply each term to get the subsequent term. So it's a term-to-term rule that we've got going on here. 3 times 2 is 6, times 2 is 12, times 2 is 24, times 2 is 48. And that's a geometric sequence as defined by this common ratio. So we're going to develop a formula for the nth term of a geometric sequence, and we're going to have a look at sums of geometric series, all using this common ratio. So we know for our arithmetic sequence, the nth term is given by un equals a plus n minus 1d. For our geometric sequence, as you can probably derive for yourselves, we're using un equals ar to the n minus 1. All right, and that hopefully makes perfect sense. If I flick back to this 3, 6, 12, 24, 48, we've got here 3, which is our first term. We've got 6, which is a multiplied by the common ratio r. We've got 12, which is 3 multiplied by r squared. So 3 multiplied by 2 squared, 3 times 4 is 12. 24, we've got ar to the 3. We've got 3 multiplied by 2 cubed, which is 3 times 8, which is 24. So you can always see that the power is always 1 less than the term. All right, so ar to the n minus 1 is our general formula for the nth term of this geometric sequence. So the problems that we're going to solve are essentially the same. All right, we've got this pretty basic one: determine the 10th and the nth terms of the following. So we've got that same sequence that we had before. And in order to solve this type of problem, it's worth writing down the information that you know. So we know that a is 3. We know that r is 2. We know that un equals ar to the n minus 1. And we use all that information to work out what our 10th term is. So we're going to have 3 multiplied by 2 to the power of 10 minus 1, which is 9. So 3 times 2 to the 9. Straight out with your calculators. 1536. So 1536. So we're now in a position using this little formula to calculate any term in a geometric sequence. The nth term, well, we've just written it down. So it says un equals ar to the n minus 1, okay, which is going to be 3 lots of 2 to the n minus 1. All right, that's our nth term for this sequence. So far, so good. Hopefully, nothing too tricky. Let's have a look at some more involved problems and some of the techniques that we'll be asking you to use to solve them. So here we're given second term of a geometric sequence. It's 4, and the fourth term is 8. We're also given this piece of information that the common ratio is positive. So we're going to have to pay attention to that. You wouldn't put it in there for no reason. And then we're asked to find some exact values. So this, again, is about writing down the information you know, and then using that information, comparing the bits that you've got to work out the bits that you don't have. So the second term of a geometric sequence is 4. So u2 is equal to 4. The fourth term is 8. So u4 is equal to 8. Now we know that for any geometric sequence, un is ar to the n minus 1. So what we're going to do is use that kind of in reverse. So u2 is 4, so un is going to be 4, and that's going to be a multiplied by r to the power of 1. All right, second term, we're going to drop that by 1, n minus 1 to give us 1. So we've got ar to the power of 1. u4 equals 8, therefore we've got 8 equals ar to the power of 3. All right, just using this un equals ar to the n minus 1 backwards in a sense, because we've got the term, we know what the position is, so we can write this right hand side in terms of those details. So then we're being asked to calculate the common ratio, all right, as an exact value. So this is going to be part A. Now, this is a feature that's common to all of these geometric sequence questions. We're going to use division because obviously as you progress from one term to the next, you're multiplying by a common ratio. So if we're trying to work backwards and find out the common ratio, it makes sense to divide. All right. So I'm just going to say, call these equations 1 and 2, each with 2 unknowns. And I'm going to take equation 2 and I'm going to divide it by equation 1. And what that's going to do is it's going to eliminate a entirely because a divided by a is just 1. And we'll see what we get. 8 divided by 4 is 2. R cubed divided by r to the power of 1 is r squared. So therefore, r is root 2. Why is it not plus or minus root 2? The common ratio is positive. So we've divided these terms, and that's quite nice because that, terms that are not even consecutive terms in the sequence, we can use. All right, we can use division just to get what we want. So we've got our common ratio. So then we're asked to work out what the first term is. So I'm just going to go back to this equation 1. All right, so from equation 1, I know that 4 equals ar to the power of 1, which means that 4 equals a multiplied by root 2, which means that a is 2 root 2. Okay, divide both sides by root 2, 4 over root 2. Rationalize the denominator, 4 root 2 over 2, which is 2 root 2. Okay? And again, we've got these in exact values because that's what we were asked to do. So now we're being asked to find the 10th term. So U10 is AR to the power of 9. We know A and we know R, so we know that U10 is going to be 2 root 2 multiplied by root 2 to the power of 9. And we can just evaluate that on a calculator, as you can do it without a calculator, but it's just, I suppose, best to make sure you've got it completely right. So we've got multiplied by root 2 to the power of 9, which is 64. So that's our, I would say, basic entry-level problem solving for a geometric sequence. We're using the properties of the common ratio to divide and calculate the common ratio. And then we're just substituting these values in to work out what we've got. Just a lot of kind of simultaneous equations work, really. All right, so we've done a bit of basic problem solving. Here's another bit of basic problem solving. I'm going to give you a couple of minutes head start on this one. I'll pause the recording. So you crack on and try and use those properties that we've described previously. You've got 3x and x plus 6, and they form the first 3 terms of a positive geometric sequence. Find the value of x. Now I'll give you a clue. You're going to first want to calculate what r is, or attempt to calculate what r is. This one. So numbers 3x and x plus 6 form the first 3 terms of a positive geometric sequence. Positive geometric sequence means we've got a common ratio r that we're going to need to work out. So we can write r in 2 different ways. We can say that r is x divided by 3, the second term divided by the first. But we can also say that r is x plus 6 divided by x. So 2 different ways of writing the common ratio. Now we're being asked to find the value of x, so it makes sense to use this information. Because those are both the same common ratio, we make them the same thing. X over 3 equals x plus 6 over x. And we're just going to multiply and solve this equation. So we end up with x squared equals 3x plus 18. X squared minus 3x plus 18 equals 0. And this factorizes, so we've got x, and we're going to have minus 6 plus 3. I factorized it right for negative 18. Boom. There we go. So we got x squared minus 6, x minus 6 times x plus 3. So x squared minus 6x plus 3x minus 18. So we've got x equals 6 or x equals negative 3. So this is a positive geometric sequence, and what that means is every term in that geometric sequence is positive, and therefore the solution x equals negative 3 is irrelevant to us because that would make the second term negative. All right, so we've got x equals 6. So for B, we're trying to find u10. Now u10 is ar to the power of 9. So we're going to need to work out what r actually is, right? Where x equals 6, what is r? So we're going to go to this one here. R is x over 3. It's the easiest one to use, which is 6 over 3, which is 2. So we've got our r. And we know that our a is 3 because it was given to us in the question. So a is 3, r is 2. So we've got 3 multiplied by 2 to the power of 9, which is going to be 3 times 2 to the 9, which is 1536 again. So again, just using those properties, the common ratio, dividing to find a common ratio, solving a little equation, and then using the information that we've got. Have a go at this one. Again, I'll give you a few minutes head start and then I'll start working through it. Sorry, getting the recording going again. So a very similar question here to the last one. Again, we're going to write down all the information that we know. We know that U3 is 20, and we can go one step further than that and say that means that AR squared is 20. Okay, we know that U5 is 80, and that means that AR to the 4 is 80. Now we've got our two equations again, and we're just going to use that division in order to find out what the common ratio actually is. So we'll do equation 2 divided by equation 1, thereby eliminating the a, and we get r squared equals 4, which means that r is equal to 2. So r is equal to 2. It's not going to be negative 2 because it says here all the terms in the geometric sequence are positive. If we had a common ratio that was negative, we'd be flipping backwards and forwards between positive and negative terms in the sequence. So it has to be r equals 2. Now we just need to work out our, so hang on a second, what's the 20th term? So u20 is going to be a multiplied by r to the power of 19. We know what r is. We don't know what a is. So we're going to go back to equation 1, use either. And if we've got that ar squared equals 20, and we know that r equals 2, that means that 4a is 20, means that a is going to be 5. Okay? So no, we're not asked to find out what a is, but we do need to know what a actually is. So u20 therefore is 5 multiplied by 2 to the power of 19, which is going to be quite a big number, which is 2621440. Yeah, just checked it. So 2621440, 2,621,440. That escalated quickly. So I hope you're seeing the kind of fundamentals coming through here. All right, we're using division to find common ratios. We're using our problem solving skills to work backwards then to find first terms, etc., etc. Okay, it's once you've got the knack, they tend to come quite quickly. So let's try the next one. Again, I will leave it to you to work this one through. It's a very similar problem. It's just extending it slightly. I'll give you 2 or 3 minutes head start. Off you go. Going with this one. So this time we've got the second, fourth, switching screens, second, third, and fourth term, sorry, right? So we've got, again, using that idea that the common ratio is something. So we've got common ratio is x plus 6 over x. We also know that the common ratio is 5x minus 6. divided by x plus 6. Find the possible values of x again. Well, those two are going to be the same, so that's what we're solving. X plus 6 over x equals 5x minus 6 over x plus 6. We'll multiply everything through. So x squared plus 12x plus 36 equals 5x squared minus 6x, and we'll rearrange that into a lovely quadratic. 4x squared minus 18x minus 36 equals 0, or 2x squared minus 9x minus 18 equals 0. So we can factorize that. And what do we get? We get 6 and 3 again. Which one's which? Let's get this the right way around. There we go. So x is going to be minus 3 over 2, or x is going to be 6. So we've got two different values for x, and it doesn't say anything about x being positive or anything like that. However, in part B, we're given the information, given that the common ratio is positive, find the common ratio. Well, if we substituted minus 3 over 2 into here, we'd get minus 3 over 2 plus 6, giving us a positive number divided by a negative number, so that would be negative, so we have to use x equals 6. So therefore r is going to be 12 divided by 6, which is going to be 2. So that's just taking 6 and substituting into this common ratio equation here. And then it says determine the possible values of the first term of the sequence. So the second term was x. So u2 equals x, which is equal to a times r. And so if x is 6, as we've said, 6 equals to a, so a equals 3. All right, so a little bit trickier, but still well within the realms of what we've been talking about. All right, so that's about as much as we can really do about nth term of geometric sequences. All right, all the problems that you're going to get are going to be kind of variations on that theme. They don't really get much more tricky than that. We need to move on then to the sums of these geometric series. Okay, remember when we write down all of the terms in a sequence added together, we refer to that as a series. Now we know that the formula for the arithmetic series is this one. Sn equals n over 2, 2a plus n minus 1b. And what we've got here is this formula for a geometric series. All right, you can see all the components are there. We've got a, we've got r, and we've got n. And one thing that you may be asked to do in the Edexcel exam anyway is to prove that result. So just like with the arithmetic series, we proved where it came from, we're going to do exactly the same with the geometric series. And it starts from making a list, just as we did before. So the sum of the n terms is a plus ar plus ar squared plus dot 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 plus ar to the n minus 2 plus ar to the n minus 1. All right, so those are our terms in any generic geometric series. All right. And that's what we're doing, all the way up to ar to the n minus 1. The term before that, obviously, ar to the n minus 2. Now, the next step is not exactly intuitive. I think proving the arithmetic series is quite intuitive. This step, I don't think is intuitive. You may disagree. We're going to multiply the sum by r, right? And that means we're going to multiply every term in the series by r. And what you should notice is that we start to have sets of terms that are matching. Right? So this AR that we've created is the same as that AR. This AR squared is the same as that AR squared. And so you've got this kind of diagonal matching pattern all the way through to the very end. Now, when we have that, it's very easy for us to then just subtract one line from the other. So if we do the top line, take away the bottom line, what we actually end up with is A minus, because there's an A on its own here, this minus this disappears, 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 and then we're just left with minus AR to the power of n. All right, it's the idea of shrinking it down so that we have fewer and fewer things to deal with. And what we do now, you're probably way ahead of me here, we can factorize. So we can say Sn multiplied by 1 minus r. You can see that's where this 1 minus r is going to come from. And we're going to factorize a from the right-hand side. And so what we're left with is Sn equals a 1 minus r to the n, 1 minus r. So there's your proof for the sum of a geometric series. All right, and again, it has come up in previous exams. It is in the spec. You are expected to be able to derive that. Don't know if I'll put it in the exam, but it's nice to see anyway. Next, we're going to look at how do we use that formula in practice. All right, and so we've got here, this is a previous exam question. We've got second and third terms, 192, 144, and then it walks us through it step by step, really. Common ratio, first term, smallest value of n for which the sum exceeds 1000. You might say that question escalates quite quickly as well, to be fair. Hopefully, parts A and B are not going to pose you too much of a problem at the moment because it's the same as the work we did on the geometric sequences. So we can say that R is going to be 144 divided by 192, the third term divided by the second term. And so 144 over 192 comes out as 0.75, I think. So let's just double check that. Yeah, 0.75. For B, if we're trying to find the first term, well, U1 is A, but is A on its own, sorry, getting ahead of myself. So U1 is A, U2, which we're given, is A multiplied by R, and that's 192. And so we're just going to use that information and say that A is 192 divided by R, which is going to be 256. Double check that. Yeah. So we've done A and we've done B. So far, so standard. Now, I've missed out part C of this question. I'm not sure why, but there must have been something in it that wasn't on the spec. So now we're going to calculate the smallest value of n for which the sum of the first n terms exceeds 1000. So let's make a bit of space for this one because its 4 marks kind of belies the complexity in a way of what we're going to need to do. So our formula, our general formula, is a times 1 minus r to the n divided by 1 minus r. We know that a is 256 and we know that r is 0.75, and what we're trying to work out is where does this sum first exceed 1000. So we're looking for this, a 1 minus r to the n, 1 minus r greater than 1000. We'll substitute in all the information that we know. So we've got 256 times 1 minus 0.75 to the power of n, divided by 1 minus 0.75, which is 0.25, greater than 1000. And from here, it's just a case of solving. So we'll multiply both sides by 0.25, and then divide by 256, so we end up with 1 minus 0.75 to the n greater than 250 over 256. Then we'll rearrange this. So we add 0.75 to the power of n to both sides. We take away 250 over 256 from both sides, and we get 6 over 256 greater than 0.75 to the power of n. All right, so hopefully you can see what I've done there. With 1 minus this fraction here, and then we've added the 0.75 to the power of n to both sides. And then how do we get this out of the power? We're going to use logarithms. So effectively, I'm saying that n is going to be greater than log to the base 0.75 of 6 over 256. You can also take logs of both sides, and that's absolutely fine. But if we do that, we've got log to the base 0.75 of 6 over 256. So n greater than, from the calculator, 13.0471 blah blah blah, and so therefore n is 14, because it's saying what's the first value of n that takes the sum over 1000. If it was 13, the sum would be just under 1000. If it's 14, it will be just over 1000. So just be careful at the end when you're using the log to solve. If you're doing log equations, be careful with your inequality sign. So yeah, that's a standard question, and we're going to move on, because there's one final thing that we need to do. Will this never end? I mean, it will, but hey. What can we say about the sum of each of these series to infinity? Now, they're all examples of geometric series. In the first one, we've got a common ratio of 2 times 2 times 2 times 2. And the second one, we've got a common ratio of minus 3 over 2, so multiplied by oh no, hang on, what is it? Minus, is it just minus 2? No, whatever the common ratio is. In fact, it's not a common ratio, so don't worry. This is just a series to infinity. And for the third one, we've got this geometric series where the common ratio is a half. So, any comments in the chat? So what you can see for these three series, the first one is divergent, the second one is divergent, and the third one is convergent. What is it about the third series that makes this series convergent? And therefore, what can we be looking out for in any geometric series to tell whether or not it's convergent? So in order for this geometric series to converge, R has to be between -1 and 1, not inclusive. All right? So we write that, much like the binomial expansion, is that mod of R is less than 1. So if we're multiplying by, in this case, a half, for example, it means that we're multiplying by a smaller and smaller amount each time. Therefore, the term that we're adding next is going to be smaller and smaller and smaller, and so that has an effect. Now, how does that affect our sum formula? It does affect our sum formula, and for one of the first times ever in maths, considering something to infinity actually makes something simple. So let's contemplate for a second, because we know that our sum formula is a times 1 minus r to the n over 1 minus r. And what we're going to think about is what happens to r to the power of n as n tends towards infinity when r is between -1 and 1. So what happens to r to the power of n as n tends towards infinity? Well, you'll have a fraction here to the power of a really large number. So we can say that r to the n is getting closer and closer to 0. And what that means then is our sum formula, if we're summing an infinite number of terms, is just going to be a divided by 1 minus r, which is brilliant. All right, it simplifies things right down for us, because r to the power of n becomes 0, a times 1 is just a. I think that's a wonderful little simplification at the end there that we use for our convergent geometric series. Now, it only works for convergent geometric series, and so mod of r has to be less than 1 for this to work. All right, otherwise it just doesn't work. All right, so have a go. All right, here's a question. A couple of minutes head start, and then I'll come back and work through it. Here we've got a problem. Again, we're given some information, but this time we're not given information about the terms, we're given information about the sums. So we're told that S4 is 15. So that means that we have a formula then, 15 equals A to 1 minus R to the N to 1 minus R. We don't know what R is, we just know that it's R. We don't know what A is, we just know that it's A. However, we do know that the sum to infinity is 16, which means we can use our other formula to write down that sum. So all we're going to do now is solve simultaneously. All right, so we've got our equation 1, we've got our equation 2. You can probably see that we can substitute equation 2 into equation 1. A over 1 minus R, we've got A over 1 minus R here. So we can say that 15 is equal to 16 lots of 1 minus R to the N, thereby eliminating the A. And then we can work out what N is. Now, this is a power of 4, isn't it? Actually, let's put that in. Anyway, so let's put that in now. We've got R to the 4 is 1 over 16. So R is plus or minus 1/2. So those are our possible values of R. We're using R4 here because we had the sum of the first 4 terms. I just hadn't put the N in previously. So then, again, our old friend, given that all the terms in the series are positive, that means that R is equal to 1/2. Otherwise, we'd be having positive followed by negative terms. And it says find the value of A. So how do we find the value of A? We can go back to 16 equals A over 1 minus R. So 16 is A divided by 1/2. So A is 32. And it looks like we're completely done. So that's the end of the video on geometric sequences and series, and I've tried to cover as many of the bases as I can about finding nth term, about finding A, about finding R. We've done the sum of a geometric series, and we've done the sum of an infinite geometric series, and we've looked at the conditions under which a geometric series is convergent. So I hope that was okay for you. Happy maths.